All right. Good morning, everyone, and welcome to this morning's ViaSatellite webinar titled Now Within Reach, Reliable Multi-Megabit Beyond Line of Sight SATCOM for Helicopters, presented by Hughes. My name is Jeffrey Hill. I'm the executive editor of ViaSatellite magazine and chair of the Satellite Conference. Thank you all so much for joining us. This webinar is going to cover some very exciting new beyond line of sight SATCOM technologies for helicopters, which my uncle, who is a retired Air Force pilot, would describe as the most complicated pieces of machinery in the sky. So that said, where would we be without helicopters? For military reconnaissance, government missions, and commercial applications ranging from extreme sports to weather monitoring, rotary wing aircraft are the most nimble means of accessing hard-to-reach and compromised sites. But sending HD video and communication from aboard these moving platforms has been all but impossible, making these ideal vehicles sometimes less than ideal in real life until now. So joining me today is Wayne Marhefka. He's the senior director at Hughes, who in a moment will be giving a presentation about Hughes' new HeloSat solution, which recently demonstrated the ability to send real-time HD video through a crisp, consistent beyond line of sight transmission. It's very, very exciting new development. We're also going to be joined by John Wellington, Chief Flight Instructor for XP Services. He is a former U.S. Army 160th Special Operations Aviation Regiment flight lead. He's flown long-range special ops missions with the 75th Ranger Regiment, Special Forces Groups, Navy SEAL teams, and Coalition Special Ops Forces, and most recently flew the successful demonstration of the Hughes HeloSat experience. And I also informed he literally just stepped off the helicopter to join us. So I'll be talking to him about his experience during the demonstration. Wayne, John, thank you so much for being with us. Good morning.
Good morning, Jeffrey. Thanks for having us for this exciting webinar. I'm really looking forward to the discussion.
Jeff, it's John. Thank you very much for having me. I really appreciate it.
Great. Thank you both for taking the time to be with us today. Just to review for the audience, so Wayne is going to give a presentation and then present a video of the demonstration that Hughes did on the HeloSat. I'll then ask John a few questions about his experience flying the demo, and we'll go to questions from the audience. For those of you out in the audience, if you have questions for Wayne or John, you can submit them anytime during the presentation through the portal that you see at the bottom of the screen. After our presentation and Q&A, we'll try to answer as many of your questions as we can. If we don't get to all of the questions, Wayne and John will reach out to you offline and try to answer those for you. So we have a lot to talk about today. Without further ado, Wayne, I'm going to turn the floor over to you for your presentation.
All right, thank you very much, Jeffrey. I appreciate the opportunity. I want to welcome all the participants. I know that based on some of my discussions with some of our partners, customers, that we have individuals from pretty much all around the world. We have our U.S. Domestic customers. We have people who have joined us, I know, from the United Arab Emirates, from India, Spain, I think Korea, Europe. So this is a really exciting time that the technology is reaching pretty much a lot of the different customers around the world. So what I'm going to go through is discuss some of the developmental aspects that have occurred over the years, some of the processes, the system flexibility, in meeting the customer's requirements. And I think the key here is that there are a lot of different requirements for getting data to the aircraft or getting data off of the aircraft. So having a system that allows the customers to meet their own individual requirements and be able to switch from platform to platform is very important. And in all of this, the complexities, we'll go through some of it, it really involves making sure that you look not only at the aircraft satellite communications, the satellite itself, the frequency bands. There's a lot of different aspects that are involved in each of these parameters, as well as the ground infrastructure and the network management that's involved in getting the data either to the aircraft or off the aircraft and then to the appropriate end users. So some of the rotor performance is, we've been demonstrating this in goes all the way back to around 2013. And a quick overview of where we're at now is that we have tested the beyond line of sight capability on a Black Hawk helicopter, which is shown in the photographs here. We tested this back in May of 2020, as well as in June. And we were able to get multiple megabits of data off of the aircraft. So the capability can be used either on Ka or Ku band. And one of the key aspects is the modem technology and the waveform, which is the waveform has really the secret sauce for the capabilities to transmit through the rotor blades. So we're going to go through several different areas here, and the challenges that we had, some of the specifications, and then going through some of the applications. The challenges in trying to transmit data through the helicopter blades has been a problem for many years, which is why you have not had broadband communications or the ability to transmit multiple megabits. So part of the problem is understanding the blade interference, or what a lot of people call the signal chop. So when you're transmitting signals through, in clear space on fixed-wing aircraft, UAVs, there's no interference in transmitting that data directly to the satellite and back down to the ground. On helicopter platforms, because the rotor blades are so large and they extend pretty much over most of the platform, is the signal gets chopped up and then you get pixelated signals, or you get signal loss. So how do you go and solve that problem? Meeting the size, weight, and power constraints are also another parameter, because on helicopters, you can see from the picture on the right, there's a limited amount of space, and every pound makes a difference. One of the issues that the military and even commercial side has had is having too much weight in the aircraft. When you start adding in people and you start adding in other pieces of equipment, it starts to add into the overall lift capability of the aircraft. And then what are the wideband or broadband throughput requirements? Is it a 1 megabit where you could get from full motion video, or do you have SIGINT, or do you have multiple speeds going into it where you require 5 to 10 megabits? So all of these are important aspects. And the last one is the airworthiness, safety of flight, and certification requirements. Now, putting something on a ground vehicle is relatively easy because you don't have to worry about the aircraft. But anytime you add something to a particular aircraft, you have to worry about the airworthiness and safety of flight. And if it's in the commercial world, you have to worry about the FAA certifications. In the military world, there's an airworthiness requirement that is necessary. So these are also very important aspects that are difficult to overcome and to take a look at. This chart, I'm just going to go through a top level part. We started this probably back in 2010 with the waveform development, where we found out from a commercial application that we had the ability to transmit data pretty much under the noise level, under the floor. So we looked at this waveform and then started in 2012 developing a very low TRL level, like TRL level 3 prototype, to see if the application would work through transmitting through helicopter blades. And it did work back in 2012. Our first flight was back in 2013 using a Bell 407 helicopter. We were able back then to transmit 10 megabits of data, but the issue was the swap of the antenna. The antenna was about 100 pounds. And we were looking at doing this for Northrop Grumman on the FireScope program. So we knew the technology worked. It's now how do you get down to a lower swap and to meet the higher TRL levels. So we evolved our modem technology, and we came up with a solid modem design with a software-defined modem in 2016. And then fast forward to 2019, 2020, we've gotten this to a TRL level 9 or production-ready system that can be put on a variety of different helicopters and been flight tested. So this has been kind of a long, evolved process, and it has involved those three different aspects, from testing on different satellites to different antenna technologies on the helicopter and then the ground infrastructure. So this is the only chart they have as far as we start looking at the future capabilities. One thing that we all want to do is keep on looking towards the future. So we know that we could do this on geo satellites very easily on Ku band what about what we're hearing today is the MEO and LEO constellations? The complexity of these gets, even much more intense because of the fast-moving satellites that MEO has in LEO. As you can see to the right, there's hundreds of satellites that are out there in orbit, and you're transitioning from satellite to satellite every 2 to 3 minutes on LEO, every 20 to 25 minutes or so on MEO, and you're constantly on the same satellite on GEO. So our customers are interested in eventually evolving all the way to LEO, which we are looking at some studies and doing this, and we're very much involved in OneWeb as far as a partner with that and developing the ground infrastructure. So what you constantly want to be doing is having the ability to evolve your system. Right now, we can definitely do it on GEO. We're going to be doing some testing on MEO and then eventually to LEO. So this is something we're always keeping in mind, our customers' current requirements as well as the future evolution of satellite communication. Okay, the next area we'll look at is some of the specifications that comes along with the design of the HeloSat system. So here's your typical GEO operational architecture: is you have a helicopter that is doing some type of surveillance on the ground and transmitting that data, or you're recording that data from an EOIR camera, transmitting it up to satellite and then back down to some ground infrastructure. Or vice versa, if you're on a mission where you require real-time intelligence information as you're en route, a ground station can transmit either video, text, or whatever is necessary up to the satellite and back down to the helicopter for those who are en route for a critical mission that would be for infiltration or going to some particular location. You also have the ability to transmit that to some ground troops. So you have to look at what is the customer's requirement for a particular mission and having that flexibility. Now, if you start looking at some of the system hardware, as we've developed all of this, we have on the left-hand side is the HM400 modem, which is a software-defined modem. It's been flight tested on the UH-60. It is also the same modem that we're utilizing for the UK Protector program, which is part of the Predator family, as well as the Gray Eagle program that USE has recently won with General Atomics. This modem is MIL standard 810G tested, so it's flight certified. Then on the right-hand side is the GetSat antenna, who is one of our key partners in all of this, because they have one of the lightest swap antennas that's out there right now. There are other systems that are capable that we put on the helicopters, but this is where we work with our end users and the customers as far as what is the capabilities you want, what is the antenna technology that you need. And sometimes there's a preference of the antenna that they want to use, which is fine. But at the moment, we've been flying the GetSat antenna because it has met most of our customers' requirements. So the A-kit and B-kit. The A-kit is a permanently installed component, the wiring that goes inside of the helicopter. On the far right, you can see some hard-mounted brackets that are inside the helicopter, and right below that is where the antenna mount would go to. So when the satellite B-kit is not on the aircraft, you can barely tell that there's anything there except for the mounting brackets that are there. The picture to the left of that is the GetSat antenna with the B-kit mounting that's on the aircraft ready for flight. The advantage of having a removable B-kit, one is you don't need it for the mission, you can take it off. For second, if you have an aircraft that's in for maintenance, you're taking the expensive piece of equipment, and you can put it on a different aircraft that's already outfitted with the A-kit. So this allows you some of the flexibility, some potential cost savings. It's not a requirement to be able to take this off. Some aircraft want to have that A-kit, B-kit permanently on there, which is a customer-driven requirement. Next, this is the UH-60 that we had permanently mounted on this. So this is the aircraft that we use for our flight test down in Tullahoma, Tennessee in May and June. During this test, we ended up having some other partners that were critical to the overall testing of it. So we had a flight concept group, which designed the A-kit, B-kit. We had XP where we had an integrated glass cockpit and weapons management system. So we're not only testing some of the capabilities of beyond line of sight, it's also the entire system architecture that would be used for the end users. Can you transmit data that's coming from the cockpit? So it was just really interesting test that we were looking at the entire system aspect. A company called CFP put various weapons on the aircraft. MAG Aerospace was supporting an L3 Westcam, had a high-definition EOIR camera that you're going to be able to see that in some of the cases in our flight tests that we were looking at targets from several kilometers away, but you could see the high definition. It almost looked like you were on top of them. So this was all kind of a critical aspect of the flight test that we did in May and June. The size, weight, and power, this gives you some of the components. As you can see, the A kit, total weight is about 8.7 pounds. The B kit that we used for this test was 53 pounds, but that included the antenna, the entire mounting kit, cables. You see the antenna was about 25 pounds. We're looking at reducing that by about 10 more pounds by modifying some of the equipment on there. So we're constantly looking at reducing the swath of the overall system. Next, I'm just going to go through several of the applications that are quite important. Because today, I think all of us understand that the thirst for data is extremely important. You know, data wasn't necessarily available to a lot of us in the past, but right now everybody wants to be connected anytime, anywhere, virtually anywhere in the world. So having data available to you is becoming more and more important. That's we're all noticing today, or in today's applications and your everyday life. So what this chart is showing is that we have successfully tested either under the rotor and several in flight on a wide variety of platforms. We tested on V-22, a CV-22, which is the Osprey in Arlington, Texas. We were taxiing down the runway and we're transmitting, I think, 6 megabits of data through those rotor blades, which are very, very large blades, but there's 3 particular blades on that platform. The Black Hawk helicopter has 4 blades, but they are fairly wide. We tested under the CH-47 Chinook. The K-MAX helicopter is another interesting one because it has counter-rotating blades, which makes the problem even more difficult. And then there's a couple other platforms here. Part of this is that we look at the various components of the helicopter, and we've been successful on every one of these. So the algorithm that we have developed is independent of the rotorcraft type, the number of blades. We do some basically blade analysis. We look at the RPM. So there is a profile set for each individual helicopter because there are differences from platform to platform, but the waveform has been successful under all these different aircraft. For some of the military aircraft that we've been looking at, the U-860, the CH-47, the S-92 is used either in the military, VIP. It's the same aircraft that is used for the presidential helicopter. But we've even been in discussions with some of the prime contractors for the next generation presidential helicopter for beyond line sight for that platform. The S-76 is another VIP aircraft that we've been looking at. So it's been kind of an exciting time in that we've been looking at all these different platforms where the technology would have direct application. The next one is, so this is very specific, you've seen these charts beforehand, is we're looking at doing another flight test where we'll be able to do about 10 megabits per second off of the helicopter. And where we put the antenna is very important from the center of gravity and looking at the installation and locations. So we work with end users on this as far as what equipment they have and where is the best place to put the equipment. The antenna has certain locations that we're limited to just based on the design of platforms. but the modem could either be put towards the aft or in the forward of the aircraft, depending on the CG requirements. Other applications, we all know that there's always disasters that are going on where your ground infrastructure may be completely taken out. So in this case, we could be flying a helicopter that has real-time situational awareness to pass that information to command centers where they can do immediate responses to send relief or emergency crews to particular locations. We're looking at it for medevac applications. So if you're in hard to or difficult locations where you don't have ground infrastructure in places like Afghanistan or other military locations, at golden hour where you could be transmitting real-time information on that patient well en route to the hospitals is a critical parameter that we could end up utilizing. There were the Hawaii volcanoes. We were in discussions and looking at and supporting those missions. So it has a wide variety of applications depending on the customers. So another one that came up based on some of the flight testing is looking at satellite communications for extreme sporting events. Places like events like the Baja 1000 that's in Baja, Mexico, there isn't the infrastructure to be able to transmit portions of this race real time. And besides, the race covers hundreds of miles. So a helicopter could be able to transmit these particular images or real-time video of the vehicles, motorcycles, up to the satellite and to a studio to be broadcasting this, where previously it was not readily available. So this is just another exciting area, and this is on, I think it was a Airbus 350 aircraft, and you can also do it on a Bell 407. Next, we've been in discussions for VIP use. The whole idea of being connected all the time from doing BTCs. And some of these helicopters you may be in a 2-hour flight where you want to maintain connectivity to various organizations or just to your staff. So there's lots of applications we're looking at it for this. Now this is the last picture. You have John Wallington on the left and Waldo Carmona, who works for ACG, who's also been flying for many years. So that's really the conclusion of the presentation. You're going to see a 5-minute video now that takes a compilation of a variety of different flights that we did back in June, and kind of gives you some of the snippets of viewpoints from inside the cockpit, of a variety of other potential situations that would be available to those who may be interested in this technology. I really think it's an evolving capability that in 10 years or so it's going to be on every platform. And this is why we're continuing to work towards evolving the product line. So I'd like to, run the video right now.
thank you so much, Wayne, for sharing your presentation and that video, which I think gives a really good visual support for all of the technology that we've been talking about today. It's pretty impressive stuff. In just a moment, we're going to get to audience Q&A. We already have a lot of questions from the audience. And just a reminder that you can still submit questions to that portal at the bottom of the screen. Those questions will come to us. We're the only ones that will be able to see your name and contact information on the question. So, feel free to submit as many questions as you can, and we'll try to get to as many of them at the end here. But before we get to that, I'd like to bring our other speaker to the floor here. John Wellington was the test pilot involved in these demonstrations. John, again, thank you for taking the time to be with us. Could you just, I know I introduced you a little bit at the beginning, but could you just give us an overview of your background for the audience?
Yes, sir, Jeff. Thank you for having me again. I spent 26 years in the Army, 14 in the regular Army, and 12 with the 160th Special Ops. From there, after I retired, I did a little work out in the oil fields, flying S-92s for PHI. And then finally ended up with XP Services, which is a independent flight test organization in Tullahoma, Tennessee. We do a lot of flight testing for different companies, and it gives me an opportunity to kind of give back pretty much to the warfighter, so still kind of helping out in that regards.
Excellent. Well, again, thank you for taking the time to share your experience with us. So, Wayne's presentation talked about how, Helosat's really kind of changing the way we communicate with helicopters. Since you have so much experience here, what has been your experience in communicating from a helicopter before the Helosat demonstration?
Well, early on, all of it's been pretty much with the 160th. We started off with a system called Rover, and then we've kind of progressed from there. But throughout, I think I did over 20-some combat tours throughout, and even did a lot of deployments down to Central and South America in support of SATCOM. We've used, ISR platforms, different satellite systems, to get, take a good look at targets before we get there, get some intel on them, keep the ground force updated, going into targets prior to us arriving there. And it just gives, everyone a great essay on what's going on. So quite a bit of work using these types of systems. But again, this is taking it a huge step further.
So knowing what Helosat was trying to offer, what were your expectations as a pilot going into these test flights? And did your experience live up to those expectations?
My expectations going in, it's all about, is the system ready to go when I'm ready to take off? We have to, or my old unit has to, take off in a moment's notice when we're deployed, and we can't wait on anything to get powered up, to find satellites, to, get connectivity. And this system, when I was ready to take off, it was ready to go. I didn't have to wait on anything. So that was an expectation that I had, and it was definitely met.
Excellent. What stood out to you? What stood out most from the experience? What was the biggest change for you?
Well, obviously, again, we've had somewhat of this technology for years, but, flying in other countries and whatnot, it's the connectivity. Sometimes you'll be on a heading in an aircraft where you're just not getting connectivity. And obviously, we plan down to the T to where if all comms go out, we continue the mission. But there's nothing like having continuous communications, uninterrupted, and throughout, our two test flights with Hughes Helosat, we had little to none connectivity issues at all.
That's great. There were two. You said you participated in two separate test flights. What were the differences between the two flights on the Black Hawk?
Well, to be honest, they somewhat were the same, but it gave XP Services a chance. We're getting ready to get a supplemental type certificate for our Genesis glass cockpit this month. And along with Tech Fusion groups, they're out of Virginia with their mission management system, and then with L3 Westcam EOS sensor MX-15 on the front, it gave us an opportunity to kind of demonstrate with the Hughes Helosat the complete capability of what our cockpit future has and what we can give to our customers. So the first one was kind of a run, kind of see if everything's working, went really well. And then the second one was all of our cockpit, the mission management system, the MX-15 and Helosat working together to provide this connectivity, throughout the world uninterrupted, and it was outstanding.
That's great to hear. So what we're going to do is, as I said, we have a lot of questions from the audience, so I'm going to try to get to these as quickly as we can. Once again, just reminding you, it's never too late to submit questions. If you have a question for either Wayne or John, please submit those to us. We'll get to them. If we don't get to your question by the end, we'll have Wayne or John reach out to you offline to see if they can answer those questions for you. And also, just to address the people that have asked, a recording of this webinar, which includes the slides and the video, will be made available to all webinar attendees following the live broadcast here. So if you're worried about missing something, you will be able to go back and view the webinar. So I'll jump into the questions. We've got a lot here about the antenna itself. So Wayne, I think most of these will be addressed to you. Wayne, is the beyond line of sight term, are you using that because the signal is not necessarily blocked by the helicopter blades?
No, we're using the beyond line of sight because there are line of sight systems. So there are microwave systems that if you have line of sight to some particular location, you can transmit data real time. The beyond line of sight is where you cannot see where the data is coming from if you're transmitting it to the helicopter, because it's going up to the satellite. So you could actually be hundreds or thousands of miles away, which is beyond line of sight, and transmitting data from a command center up to the satellite and down to the helicopter, and vice versa from the helicopter to the satellite up. So if you're at a forward operating base and your crews are hundreds of miles away, you could be getting real-time information beyond line of sight or beyond even line of sight systems. So it gives you a much more capability to transmit basically data around the world.
Okay. Wayne, I'm also going to ask you a couple of questions about the antenna here. First, somebody just asked what antenna is being used, and then also what are the minimum antenna RF requirements for both KU and KA systems?
Well, the antenna that was used on this particular flight test was a GetSat antenna, and they have a variety of different sizes depending on the requirements. The antenna that we used was called a MilliSat High, so it kind of looks like almost like a top hat. There's an antenna that's half the size, but when you cut this antenna size in half, you get half the data rates. So it all ends up being based on the customer's requirements and what do the end user really want to get either to the aircraft or off of the aircraft. What we found is based on link budget analysis is that the GetSat MilliSat is the optimum system, particularly for a Black Hawk or for these mid-size to larger size antennas or something in that caliber. So when you start talking about what is the appropriate size of the antenna, it really depends a lot of times on the satellite as well, because the satellites have what they call an ERIP and a gain over temperature, which is basically the power of the satellite. Older satellites have less power, so you need to have a larger size aperture or higher gain from the antenna. The antenna technology you have to be a little careful with because there's a bunch of satellites that are orbiting out there in the smaller the satellite, the wider the beam. And so what ends up happening is you can have adjacent satellite interference, and you don't want the international ITU standards don't allow you to excessively transmit power to may affect the other satellites that are out there. So you have to stay within standards. And so this is kind of where all the analysis comes in, is what are the requirements, and that goes and drives some of the antenna technologies. What is your area of operation? Because testing it in the United States, where there may be a very powerful satellite, it's not the same thing as what you may get in Afghanistan or some other place, or in Asia Pacific, where there's a lot more issues with range. So KU band sometimes is better. In other locations, KA band. So it's kind of a really difficult question to answer because of a lot of parameters. This is why I say that you have to take a look at the entire architecture, from the satellite to what's in the aircraft, or on the aircraft to the ground infrastructure. Because even your ground antenna plays a role into your data rates.
John, this next question I'll throw to you. Did any of the flight tests that you participated in include assessing performance during tactical environment where the platform is making harsh flight maneuvers?
Yeah, both test flights. Obviously, especially with the mount that we put on the back, we first tested that and put the aircraft through a bunch of different maneuvers for structural purposes. And then once we've got everything mounted, and we're doing the video push, we banked the aircraft, turned the aircraft a bunch of different directions, made sure that we had connectivity, all the time.
Excellent. Thank you, John. Another question for you, Wayne. Are mechanical or electrical phased array antennas going to be required to support MEO and LEO capability? That's medium and low Earth orbit. For those of you who don't know, what is your roadmap for MEO and LEO products?
Well, I mean, that's actually a very good question, because as I mentioned in the one chart, the complexities from handoff from satellite to satellite greatly increase as you're going to MEO, then even more so with LEO. So one of our CEO has already stated that our partnership with OneWeb is that he sees that augmenting the GEO capability with the LEO, because LEO will now give you polar coverage. And it gives you coverage in areas where we may not have coverage, or others may not have coverage with GEO. So there is a roadmap that we're looking at that goes and addresses the Doppler compensation, not only from the mobility, because right now when we're flying on the aircraft, we have to worry about the Doppler based on, which is the movement of the aircraft moving along. But now you have the movement of the satellites. MEOs, which are the mid-Earth orbit ones, are moving very fast. The LEOs are moving extremely fast. And so you're handing off from satellite to satellite every 2 to 3 minutes. And so it affects not only the antenna technology to do the handoff, so this is where your electronically scanned arrays come into play that are going to be a requirement for the LEO operations, but mainly because of the beam switching, and mechanically a parabolic or antenna that is on a gimbal spinning around has difficult times locking onto the satellite and switching onto the other one every 2 to 3 minutes. For GEO, you're constantly looking pretty much at the same location, so it's very easy to do. So we are in the process of developing improvements to the modem technology, as well as investigating other antenna technologies. There are companies out there to include GetSat, Ball Aerospace. ThinkCom has a different type of antenna that I think is that's flying on commercial airlines now that would have some direct applications. And there's been some testing initially on MEO and some initial testing on LEO. So we're evolving towards that because, again, it's going to, depending on your mission requirements, and you switch from one constellation to the next. So all of this is in the roadmap because that's where technology is going.
Thanks, Wayne. I'll direct this next question starting with John to talk about the experience, and then Wayne, maybe if you want to jump in afterward and talk about more of the technical aspects here, but how does this system differ from current L-band systems deployed on rotary wing aircraft today? John, talk about the experience. How is it different? And then maybe Wayne, you can talk about the technical differences.
Again, it's all about the connectivity and the uninterruption. Certain headings that you're flying, you've got to get that thing pointed a certain direction in order to get that good connectivity. With this one, any direction that we turn, we always had it, and so to me, that's the biggest difference.
So from my perspective, I'm sorry, go ahead.
No, I was just going to ask Wayne if you wanted to jump in.
Yeah, from my perspective, we've looked at the L-band solutions, KU, KA band. The L-band solution has this application or its place in some of the mission requirements. But typically, you're going to be getting lower data rates. One thing that we had talked about here in utilizing some of the more powerful satellites, like the Inmarsat MIL-KA movable spot beams, we're going to be able to get 10 plus megabits. We think we may even be able to get up closer to 20 megabits, depending on the various parameters and how you look at it. You're not going to get there with the L-band systems. They do have their place in the overall architectures, but then you also have to look at the cost of ownership. To get high data rates on L-band, I think you're going to end up having a more costly system. There still is the issue, of going through the rotor blades. So I'm not an expert on it, but I think there's a place for each of them, depending on what you're trying to do. But at the higher data rates, I think you're getting into the systems that we're testing here, the KU, KA band. There's an over-horizon, what's it called, 30B frequency band, which is very applicable to some of the COCOMs, the combatant commands that are utilizing that frequency band, as well as the MIL-KA. So, it's a little bit more from a technical standpoint. I think there's a time and place for each, but higher data rates, you're really going to need the technology for through the road.
Again, another question for you, Wayne. You stated the system has to be tuned for each helicopter or rotor type. How does this impact the modem on the distant end? Will different modems and waveforms be required at the GEP to support different helicopters?
No, it's the same modems as far as it's the same modem on the ground versus the same modem in the air. Is what we end up doing, and we're looking at having an automatic adaptation. So if we're putting it onto a Chinook, we know what the RPMs of that blade, what that helicopter is, what the blade width is, and so we develop a profile. So basically, on a user interface, we can go and have a whole slew of basically a library of profiles. So if you're putting your system on there, you go to your handheld computer, you say, all right, I'm on a UA60 or I'm on an NH90 or whatever the platform is, and you just choose that profile and it's automatically there. As we start to evolve this in our roadmap, is you're going to have like an automatic adaptation to do this because it's a software-defined modem. So, today, if I'm going to go put it on I've tested under NH90s, MI17s, and they all have different characteristics and they all work, but we made sure that we had the correct profile for that platform. It's just not an automated system at the moment, but it's not a difficult thing to do. We can do it relatively, in a day or so, once we have the data from the helicopter.
All right. This next question, John, I'll direct it to you to start. Though, again, Wayne, if you want to come in here with any technical information, that would be very helpful. But this question refers to the radome location on the Black Hawk. The S70M Hawk derivative has 2 GPS antennas on the tail drive shaft cover. Are there any concerns from the pilot with this system being mounted near those GPS antennas? John, I'll start with you, and then Wayne, if you want to jump in, that'd be great.
Well, we did all of our testing on an old EH60. And again, we've installed a new glass cockpit with Genesis into this aircraft. And our GPS antennas are up just after the APU opening there, and not on the tail boom or the drive shaft cover. But we did all the EMI testing on it, and we had no loss of GPS signal whatsoever through our system.
Yeah, so John is absolutely correct. Okay? So we also did some testing. So we're putting a get that antenna onto a C-27 U.S. Coast Guard aircraft, and there were probably about 10 or 15 other antennas on that aircraft because of the mission that it did. And we had to do all the EMI analysis, and there were no effects on it. Most of the time that these other antennas are at different frequency bands, so they're not interfering with each other. But the analysis has been conducted and would be conducted on other platforms to make sure there's no interference, but we have not experienced any up to this point.
Wayne, this question will be for you. Is it possible to mount the antenna on top of the rotor hub to avoid blade blockage?
So the answer is anything is possible, but the cost of in doing that, you have to end up having a hollow drive shaft because you do have to have some cables powering everything going through. Some helicopters have that hollow drive shaft, and some don't. So it's possible, and there's been others, and I can't remember the exact military helicopter that's put something up there. But you start to get into a lot of mechanical designs. And so what we try to do on ours is basically have a roll-on, roll-off capability, which is why, you have a permanent A kit, but you have a removable B kit. The modem technology and everything is inside. What we try to avoid is any integration into the major avionics that are required to fly the helicopter. Because once you do that, you get into a recertification of the entire aircraft. So what we're trying to do is have the least invasive system that will allow users to have the flexibility without incurring a significant cost in recertifying their aircraft. Getting the basic certification has its own cost, which we've been working towards, and we have a certification for the UH-60A that we've been flying on through the FAA. So the answer is yes, you can, but it ends up being a real big cost driver.
Wayne, another question for you here. Could your technology be used as an XL node in an airborne networking scenario of manned and unmanned platforms?
The answer is yes. So you can, under the command-unmanned teaming, we are providing a data pipe. So the ability to transmit data to other platforms or receive data from other platforms is always there. That just has to be involved in the overall architecture design, because what we really are is a data transport mechanism. So if there are other data transport mechanisms out there that ability to transmit and receive, you absolutely can talk to them. You just have to have the correct interfaces and work through the technical issues. Is it technically feasible? The answer is absolutely.
Also, another one for Wayne. Can you talk about if there are some special certifications required for different helicopters to install the satellite terminal?
Well, there's as I mentioned a little bit in the presentation, so depending on the platforms, there's a FAA certification required if it's a commercial aircraft, or a airworthiness requirement for a military aircraft. They're both similar in nature as far as the processes required. So once we put it on to, say, the Black Hawk, the certification that would be required for a Chinook or, say, an NH-90, which is more similar towards a Black Hawk, what we would do then is use a Delta certification. So if there are similar methodologies that are applicable to both because of helicopters, a lot of that documentation may be directly applicable. So there may be a 10 to 20% additional work for that particular platform, so your cost is reduced to get that certification. But a lot of times I look at is the equipment that you're putting on there certified, from the antenna, the modem, the cabling, what are you doing structurally? So a lot of those things are going to be relevant from platform to platform, but there will be some uniqueness to the different platforms, but it's not like starting from the beginning.
All right, and this will be our last question for the webcast here. But Wayne, how does the range of the system differ from current line of sight systems such as the TCDL rover? Are there any limitations in low-level flight in canyons?
Well, the limitation that you have is that the satellite, the antenna on the helicopter has to have line of sight to the satellite. So in most cases, since the satellite is the geos are 25,000 miles up, is that you have, most of the time you have line of sight to this platform, so there aren't very much limitation. The line of sight systems, you're limited to line of sight. So when they're flying helicopters off of Navy platforms and they're flying into inland, and there's a mountain range there, as soon as they go over that mountain range, they lose connectivity. This is why they were looking at the Fire Scout 8C, which is the newer platform based on 407s, that they would like to have beyond line of sight, because otherwise they're limited to the line of sight link. And so the lower you go based on the curvature of the Earth, the less range you have. If you're higher up, you get longer range. But typically you could say your range is in the 80 kilometers. If you're high altitude, it'll be longer. But beyond line of sight really gives you the flexibility to transmit, kind of like some of the Predators are doing now. They're operated from the U.S. for operations that are overseas. And that's all beyond line of sight. So basically what you're doing now is giving helicopters the capability, the broadband capability that they have not had before, that fixed wing and UAVs have had. So they were kind of a disadvantaged platform because of the rotor chop. But we've solved that problem, so now they can be part of the group that has real-time valuable information to do whatever that mission is, from surveillance to medevac to firefighting. Gives a lot of flexibility to end users to have an added capability that previously was not there.
Excellent. Well, all right, thank you so much. That's all the time that we have for today. As I said, if we didn't get to your question, our speakers will respond to you offline. Wayne, John, thank you so much for your time. Thank you for that excellent presentation, for answering questions for us today.
Thank you for having me.
Thank you.
Once again, thank you, guys. Once again, my name is Jeffrey Hill, Executive Editor with ViaSatellite. I hope you enjoyed this morning's presentation, sponsored by Hughes. So thank you so much, Hughes, for sponsoring this. And thank you all in the audience for joining us. Have a great day. Stay safe and healthy, and we'll see you soon.